Welcome back to Java Internals Crashcasts. I'm Sheila, and with me, as always, is Victor. Today, we're continuing our exploration of synchronization utilities in Java. We're in the third chapter of this season, focusing on atomic variables. Specifically, we'll be diving into AtomicInteger, AtomicLong, and AtomicBoolean.
That's right, Sheila. These classes are fundamental building blocks for writing efficient, thread-safe code without using explicit locks. They're part of the java.util.concurrent atomic package, which was introduced in Java 5 to support lock-free, thread-safe programming on single variables.
Before we dive in, let's start with a quick quiz for our listeners. Here's the question. In a multi-threaded environment, which operation is guaranteed to be atomic when performed on a regular integer variable? Is it A, increment, B, decrement, C, assignment, or D, none of the above?
Ooh, that's a great question, Sheila. It really gets to the heart of why we need atomic variables in the first place. Listeners, take a moment to think about it. Consider what happens at the processor level when you perform these operations. We'll reveal the answer at the end of the episode.
Excellent, Victor. Now, before we get into the details of AtomicInteger, AtomicLong, and AtomicBoolean, could you give us a quick refresher on what we mean by atomic in this context?
Certainly. In concurrent programming, an operation or a set of operations is considered atomic if it appears to occur instantaneously from the perspective of other threads. In other words, no thread can observe the operation in a partial or incomplete state. It's all or nothing, with no possibility of interference from other threads.
That's a clear explanation. So, how do AtomicInteger, AtomicLong, and AtomicBoolean fit into this concept?
These classes provide atomic operations on their respective primitive types, int, long, and boolean. They allow you to perform reads and writes, as well as more complex operations like compare and set, all in an atomic manner without the need for explicit synchronization.
I see. So, if I understand correctly, using an atomic integer instead of a regular int would allow me to increment or decrement its value safely in a multi-threaded environment.
Exactly. Let's take AtomicInteger as an example. It provides methods that perform operations like incrementing, decrementing, and adding atomically. This means you don't have to worry about race conditions or inconsistent states that could occur if multiple threads tried to modify a regular integer simultaneously.
That sounds really useful. Can you give us a real-world example of where we might use these atomic classes?
Certainly. One common use case is for generating unique IDs or sequence numbers in a multi-threaded application. Imagine you're building an e-commerce platform where multiple threads are processing orders simultaneously. You could use an AtomicLong to generate unique order IDs without the risk of two orders getting the same ID.
That makes sense. Now, you mentioned something called compare and set earlier. Can you explain what that is and why it's important?
Of course. Compare and set, often abbreviated as CAS, is a fundamental operation provided by these atomic classes. It's the secret sauce that allows them to perform lock-free atomic updates. The idea is simple. You check if the current value is what you expect it to be, and if it is, you set it to a new value. All of this happens in a single atomic step. If the current value isn't what you expected, meaning another thread may have changed it, the operation fails, and you can decide to retry or take a different action.
That's fascinating. It's almost like a peaceful handshake between threads, making sure they're on the same page before making changes. Can you give us an example of how we might use CAS in practice?
Absolutely. Let's stick with our e-commerce example. Imagine you have a product with a limited stock, represented by an atomic integer. When a customer tries to make a purchase, you might check if the expected stock is available, and if so, decrease it by 1. If the stock has changed since you last checked, you might retry or inform the customer that the item is no longer available.
That's a great example, Victor. It really illustrates how these atomic classes can help prevent race conditions in real-world scenarios. Now, I'm curious about the performance aspect. How do these atomic operations compare to using synchronized methods?
That's an excellent question, Sheila. In general, atomic operations are much more lightweight than synchronized methods. They use low-level, hardware-specific instructions to achieve atomicity, which is typically much faster than acquiring and releasing locks. However, it's worth noting that in high-contention scenarios, where many threads are constantly trying to update the same variable, atomic operations might lead to many failed CAS attempts, which could impact performance. In such cases, other synchronization techniques might be more appropriate.
I see. So it's not always a clear-cut choice. Are there any common pitfalls or best practices we should be aware of when using these atomic classes?
Absolutely. One common pitfall is using atomic variables for compound operations. For example, if you need to increment a value and then perform some action based on the new value, you might be tempted to do it in two separate steps. However, this is actually not atomic as a whole and could lead to race conditions. Instead, you should use the atomic variables methods to perform the entire operation atomically. As for best practices, it's generally a good idea to prefer atomic variables over synchronized methods for simple operations on single variables. They're more efficient and can lead to more scalable code. However, for more complex operations involving multiple variables, you might need to consider other synchronization mechanisms.
Those are great tips, Victor. Before we wrap up, could you briefly touch on the memory consistency effects of these atomic variables?
Certainly, atomic variables have strong memory consistency effects. Any write operation on an atomic variable has the same memory effects as a volatile write. This means that updates to atomic variables are always visible to other threads, and there's a happens-before relationship between a write to an atomic variable and any subsequent read of the same variable. This is particularly important in the context of the Java memory model, as it ensures that other non-atomic operations that happen before the atomic operation are also visible to other threads.
Thank you, Victor. That's a crucial point for developers to understand. Now let's get back to our quiz question from the beginning of the episode. Victor, would you like to reveal the answer?
Of course. The question was, in a multi-threaded environment, which operation is guaranteed to be atomic when performed on a regular integer variable? And the correct answer is D, none of the above. While it might be surprising, even simple operations like assignment are not guaranteed to be atomic for regular inti variables in Java, especially on 64-bit systems. This is why we need special classes like AtomicInteger when we want to ensure atomicity in multi-threaded scenarios.
That's a great reminder of why these atomic classes are so important. To wrap up, let's quickly summarize the key points we've covered. 1. AtomicInteger, AtomicLong, and AtomicBoolean provide thread-safe operations on their respective primitive types. 2. They use compare and set, CAS operations to achieve lock-free atomic updates. 3. These classes are generally more efficient than using synchronized methods for simple operations. 4. They have strong memory consistency effects, similar to volatile variables. 5. While powerful, atomic variables are not a silver bullet and should be used appropriately based on the specific concurrency requirements of your application. In our next episode, we'll be diving into atomic reference and atomic array classes. Until then, keep coding, and may your threads always be in harmony.
Absolutely, Sheila. And to our listeners, thank you for tuning in to Java Internals Crashcasts. If you found this episode helpful, please subscribe to our podcast and leave us a rating. Your support helps us continue producing these in-depth explorations of Java's internals. See you next time.